generally related to the idea of weighted edges is trying to find the optimal path between one node and another. So for example, if I want to get from node 0 over to node 4, what way can I do that using the least amount of edge weight possible? That might be an example of a problem we want to solve. And when we're trying to do that, we're taking a look at something known as the shortest path problem. With the shortest path problem, we generally are trying to find the shortest possible path from one node to another. The definition of shortest path can change generally depending on what kind of problem we're working on. For our particular example, what I'm going to say is that the shortest path is the one that minimizes the edge weight. So that gives us the smallest possible edge weight. And you'll see in some cases edge weights might be negative, or edge weights might be positive. Positive and negative edge weights can mean a variety of different things. In this example here, basically what I'm saying is that negative edge weights, since we're trying to minimize the size of the edge, negative edge weights would be good. If we could traverse a negative edge weight, it would decrease the actual weight, which would be beneficial for us. However, in some cases, we may want to try to maximize our edge weight, in which case negative edges may not be a good thing for us. So they could vary based on a variety of different things, but generally the idea here, again, is just that we have a bunch of edges, a bunch of weights, and we want to find a way to get from one node to another following these different weights, right? So the idea of what we're going to be taking a look at is algorithms that can tell us what the distance is from one node to any other node in the graph, and it will help us minimize the actual paths themselves. So for example, if I were to take a look at starting at node 0, I could figure out the shortest path from 0 to itself, from 0 to 1, from 0 to 2, from 0 to 3, and from 0 to 4. We call this a single source shortest path. Basically, we start at a single location, and we try to get to all of the other nodes, and we determine the shortest path or the smallest amount of edge weight required to get to each of these nodes. So in these examples, like 0 getting to itself, since we start at 0 and we end at 0, we don't traverse the edges, so we have a total of 0, right? The only way to get from 0 to 1 is to traverse the edge between them, which would give us the value 5. To get from 0 to 2, we have basically two options. The first is that we traverse from 0 to 1, so that always happens. So we always have a weight of 5. But then we have to consider, should we go from 2 to 3, or from 1 to 3, right? This would give us a weight of 2, and we wouldn't be able to move from it. So that's not a good solution. But we could go from 1 to 2, which gives us a value of 1, right? Giving us a total edge weight of 6. So that would be the minimum possible value. From 0 to 3, we have a similar type of thing, right? We go from 0 to 1, which gives us 5, right? Then we have to decide, do we go from 1 to 2, or from 1 to 3, rather, right? That would give us a total of 2, which would be equal to 7, right? Or we could go from 5 to go down from 1 to 2, right? Which would give us a weight of 1. And then we could go from 2 to 4, which would give us a weight of 1. And then from 4 to 3, which would subtract 1. Right? This would give us 6, plus 1 would be 7, minus 1 would be 6. So that's actually the minimal, would be a value of 6, which would be going from 0 to 1 to 2 to 4 to 3. Do you see how sometimes we get a bit of a roundabout way, especially when we have negative edges, right? Those are a little bit tricky. And the final one is from 0 to 4, right? This one is going to be, we have 5, and then we would generally go 1 and 1, which would be 7, right? So that would be the only way to get to 4. So these are the minimum possible ways to start at 0 and get to another node inside of the graph. That is the general idea of what we're trying to do. We're trying to map out all of these different solutions for a given graph. Starting at one point, ending at the other, how do we minimize the edge weights? We're going to explore two different algorithms to do this. The first is the Bellman-Ford algorithm, and then the second is Dijkstra's algorithm, which is a very famous graph theory algorithm. So we're going to take a look at both of these approaches, and we'll see how they generally work in the next few videos. So thanks so much for watching. I'll see you in the next one.